Today we will be going over the history of electromagnetic testing, starting back in 1879 with David Hughes. That gentleman invented one of the earliest ET devices called the induction balance, and he didn't have the complex electronics that we have today, so he had to use what was available to him. So he used a microphone, an electric sonometer, a telephone, and a battery. He used his simple induction balance to sort different types of conductive materials. Hughes initially used his inductive balance to test coins, and when comparing similar coins, minor wear, temperature changes, or alloying differences between the coins would cause an imbalance in the circuit. Take a look at the list on the right. It should look familiar, as the International Annealed Copper Standard has very, very similar metals and conductivities. So I'm sure that the current International Annealed Copper Standard ratings were based on Hughes' early work. Now, ET got its beginnings back in the early 1900s. I believe it was in the 1920s, when there was a horrific train crash and there was several fatalities. So the railroad industry started looking into ways to test their wheels and their tracks so similar catastrophes could be avoided. This image here shows one of the very first photographed industrial systems where ET was used to examine steel pipes for cracks. This image shows the first commercial installation of an ET system in Pennsylvania to inspect steel bars for Union Drawn Steel Company. That was 1934. Dr. Foerster, known as the father of modern eddy current testing. Dr. Foerster is based out of Germany, and he was working on several electromagnetic induction or eddy current comparators that he patented in the United States from 1925 until the end of World War II. Around that time, many technological advancements were made because they were making, ships and tanks and bullets, and all of those things needed to be inspected with non-destructive testing. And this is when eddy current testing really started to be developed. Dr. Foerster was known for his very sophisticated and very precise ET equipment early on in the development of electromagnetic testing and eddy current test instruments. Dr. Foerster's work serves as the foundation for what is known as impedance plane phase analysis. This is an image that many of you have probably seen showing a hysteresis curve or hysteresis loop. Well, that image that you see in most publications was developed originally in Dr. Foerster's ferrograph. Dr. Foerster uses ferrograph to generate magnetic hysteresis curves, which provide information on the magnetic properties of a material. Now take a look at that picture. Those are a bunch of tiny parts that were used, that were tested with some of Foerster's instruments. He actually used the multi-test system routinely for testing large volumes of these tiny sewing needles, drill bits, watch springs. Can you imagine how small a watch spring is? Ball bearings and materials down to 1/1000th of a gram could be tested and sorted. Dr. Foerster's multi-test systems were used in many factories across Europe to examine large volumes of various parts. Here we see two Foerster multi-test systems used in a ball bearing manufacturing facility. Foerster's multi-test system was able to sort over 10,000 ball bearings per hour based on varying magnetic properties. Now, imagine this is back in the 50s probably. And with his testers, he was testing 10,000 ball bearings an hour. That's pretty impressive. Dr. Foerster's system incorporated circuits for calibration checking and statistical evaluations. And if you can look at this picture here, he's got the tester on the left and a conveyor belt, and then he has some sorting mechanism that sorts the parts into 3 different buckets based on different material properties. Dr. Foerster's MagnaTest Q was used in conveyorized systems and could sort between 3,000 and 8,000 parts per hour, depending on the size of the test part. Now we're starting to get into early phase analysis. The multi-test instrument shown here is displaying the impedance vector points for varying degrees of hardness of pressed parts. Foerster's StataMat statistical control system was used to show the frequency distribution of the various hardness values. So if you look at that image in the upper right that's circled with the dotted red circle there, or dash, you'll notice a bunch of different points on the screen. Many eddy current training publications will talk about historical methods and the vector point method. Well, each time a part was tested, the impedance dot, that's the thing that moves all across, even your modern eddy current instruments, that little trace would show on that screen in the form of a dot for each different material tested. So there's probably hundreds of different parts being tested, each showing a specific impedance point on the impedance plane. And of course, all that information was fed into the StataMat, and he could see the distributions of the different type of parts based on the property. Here we see a cathode ray tube used that displayed more than one object parameter by displaying changes to amplitude and phase. So on this tester from Foerster, you can see a sine wave. And this method was used in something called the time-based method, the linear time-based method. Foerster's MagnaTest Q was used in conveyorized systems and could sort between 3,000 and 8,000 parts per hour, depending on the size of the part. Here again, you'll see a conveyor belt and some sorting buckets. But what the testers would do when they were using this instrument, if you look in the upper right-hand corner there, that's an illustration of an oscilloscope, and there's a sine wave in that display. And what happened was that sine wave would move to the left and to the right. And if you look in the lower right picture, right above the picture of me, or the video of me, that's the actual test instrument that the operator was looking at. The linear time-based method was used extensively for material sorting. So what they would do was, during the calibration, they would take a little piece of see-through plastic or cellophane, and they would record where different known material properties would show up on the display. They would then take a colored pencil or marker, and they would draw those sine waves on the piece of plastic. So some of the pieces of plastic would show a sine wave representing a rejectable material, and a different color may represent rejectable material. And by taping those cellophane images up on the screen, they had an easy reference point that they could use as they were loading parts, into the test apparatus. Here we see, looks like ellipse on the right-hand side there. Dimensional variables would alter the angle of the ellipse, while a conductive change would change the opening of the ellipse. Just about every eddy current test will have some questions on vector point and the ellipse method. Again, these are historical methods that we don't use anymore, but it's interesting to discuss them. This slide shows you some of the various changes that can be noted with the ellipse test method. Again, if the line doesn't open up into ellipse but it tilts, that would be a dimensional change. But if that line starts opening up into a circle underneath ellipse, that shows conductivity change. So if you have an increase in the angle and an opening of the ellipse, then you have a change to dimension and conductivity. Now, I like this particular slide because it shows the first known image of an impedance plane with some impedance plane signals. This came out of Dr. Foerster's lab in 1942, it looks like. This is pretty significant because impedance plane instruments in the U.S. were not known to be developed until sometime in the 50s. So Foerster was at least a decade ahead of the States. As the European economy grew after World War II and grew stronger, testing of industrial materials increased rather quickly. The number of parts such as rods, tubes, and automotive parts tested in Europe daily in the 1950s was over 5 million parts. Actually, by the end of 1956, over 5 million parts per day. That's not per month or per year, that's per day. So Dr. Foerster's instruments were getting a lot of publicity because they were being used to solve a lot of industrial problems. Once Dr. Foerster's instruments were accepted by the industry, this fueled meteoric growth of new applications of ET, particularly from 1950 to 1965. Due to his pioneering work in the field of eddy current testing, Dr. Foerster is often referred to as the father of modern eddy current testing. That's not to say that there weren't some very brilliant people that came after him that further developed his craft, but he definitely laid the groundwork. So while Foerster was working on his impedance plane instruments back in Germany, in the USA, Shell Oil patented this thing called the probolog, and it was used to inspect non-ferrous heat exchanger tubing in the mid-1940s. Now, once tubing is installed in a heat exchanger, it must be inspected with inside bobbin probes because that's the only way you can access the interior of the tube. If it was in a factory, you could feed the tubes through an encircling coil, so it's much more convenient. But when they're installed, you got to use an inside probe, and you can pull the tubes by hand, you can pull the probe by hand, or you can use a mechanized probe driver, which is the preferred way to go, especially if you have large numbers of tubes. The probolog did not use an oscilloscope, and it didn't use impedance plane traces. It used a paper strip chart, and that's what the operator would look at to evaluate the data. Well, when you have a strip chart, that's very limited information. So if you saw a big kick on your strip chart, well, it'll probably tell you that something's going on. Could be a great big dent, or could be a great big hole. But based on the strip charts, the operator would have to make some sort of decision. Those, of course, were single frequency testers. Now, by 1950, several different types of test systems based on electromagnetic induction were being used for industrial applications. The Sperry detector was used to detect longitudinal flaws in ferrous and non-ferrous tubes, rods, and bar stock. Dr. Foerster's development of the law of similarity and associated impedance graphs were groundbreaking in terms of understanding the relationships between material properties and their effect on test coil impedance. In the early 1950s, a few American scientists who were able to read German started to learn about Foerster's work. Now, the similarity law developed by Foerster was his way of determining how you could manipulate the test frequency to obtain certain effects. The similarity law used a formula developed by Foerster that you'll see in just about every, at least advanced eddy current tests. So you'll need to know that formula, but once you know the formula and this thing he called the limit frequency, you could find any variable that you wanted based on his impedance graphs and his similarity law. That's mostly subject matter for Level 3 exams, but it's very interesting to know the origin of the similarity law, Dr. Foerster. There was a man by the name of Richard Hochschild. He made a visit to Germany probably 6 months or so to Foerster's laboratory. And when he came back, he basically did a data download and he started writing a bunch of reports. And at this time, he was working for the U.S. Atomic Energy Commission, who sponsored his visit. These reports were distributed to various labs across the USA, where development of new instruments based on the intelligence that he gained from Germany began. And here we have the cyclograph. This test setup used a DeMont cyclograph Model C with an external chart recorder and was used in testing to support fatigue predictions. The image on the bottom shows the test piece protruding from the right end of the test rig. Of course, it's blocked by my image, my video. But the cyclograph coil is surrounding the test piece. Now that's interesting. The cyclograph is using an encircling coil, and I learned after I made these slides that they started trying to develop some tests where the cyclograph could be used with the bobbin coil, but the way the cyclograph was designed, it didn't have the capabilities electronics-wise to support small bobbin coils. It was mostly used for larger coils. Then we have the Radak. This was in 1960, and the Radak had punch card programmable devices, I guess you call them. But punch cards were used to program the Radak. And the Radak was used in modulation analysis. This was actually probably the predecessor to modern day automated screening tools. So in modulation analysis, the Radak tester used complex filters to separate signals of interest from unwanted variables such as probe wobble. So on the top, you got a bunch of noise and hash, but buried in there somewhere is the signal from a flaw. So during the modulation analysis, the electronics, and you use this thing called the Fourier control switch, where you could sort of dial out some of the stuff you didn't want to see and dial in what you did want to see. And then when you got your filtering, set just right, it would be achievable to find flaws. Now, in 1964, a man by the name of Hugo Libby, he was another pioneer. He was working at the Hanford Labs up in Washington State, and he developed a new tester for the marketplace. And this is really, at least in the U.S., the technology that really started it all and is the predecessor to what we currently use. This unlocked the true potential of eddy current instrumentation. So here you see a tube with a bobbin probe in it hooked up to an oscilloscope where you have the differential signal on the impedance plane and an external strip chart. That's what we use today, Lysiju's and strip charts for all tube testing. And of course, that data is displayed and evaluated on an impedance plane. Why an impedance plane instead of a strip chart? Well, the impedance plane, when you compare it to like an impedance magnitude tester, analog, an impedance magnitude tester just has a needle on it. And if the needle moves, something changed, right? But you don't know what. You just know there's something changed. But impedance plane, you can tell not only the amplitude of an indication, you can also see the phase angle. And the phase angle of the signal is based on the depth of the eddy currents that are displayed or disturbed in the test material. So if you look at the image on the left, you'll see 1, 2, 3, 4, 5 different signals. Those are the different signals from the calibration tube. And as you can see, each one of them has a different phase angle. And that's, one of the attributes of the signals that data evaluators are trained to interpret. Now, the 1970s in the States, that was a big decade because that's the period when several industries started to realize just how well suited eddy current testing was for meeting crucial inspection needs. Those companies were heavily invested in the development of more advanced eddy current testing instrumentation and applications. Several government-funded laboratories were also performing research and development of various eddy current testing applications. So if you go to the website eddycurrent.com, that's my website, there is a tab somewhere on the website that talks about research facilities. If you go to that tab, there's going to be links for like the Hanford Lab, Oak Ridge National Laboratory, Savannah River National Laboratory. In Canada, you got Chalk River. There's Sandia Labs. In the U.S., there's probably, 15, 20, probably more. But that's where I got a lot of the information for these slides, number one. But all those government labs were doing research. A lot of it was top secret at the time because the technology was being used to inspect components in nuclear power plants. So because of the nuclear aspect of it, it was all very secretive. And, we were in a race with other countries to see who could test the most, the best, the fastest, and the most accurately. Industries such as nuclear, automotive, petrochemical, and aviation industries were able to take advantage of eddy current testing. It's fast, it's accurate, there's not a lot of surface preparation, and you can find very tiny flaws. Up until the late 1970s, test instruments were limited in that they were only capable of testing one frequency at a time. And a lot of current testers only use one frequency at a time. A good example is if you're, scanning, just if you're scanning and doing surface testing and you're looking for cracks, you might just be scanning with one test frequency. But then if you find something, most modern instruments, have the capability to look at different frequencies. When you get into some of the more advanced testers, you can select, numerous frequencies. But for standard bobbin tube testing, 4 frequencies is enough. By the late 1970s, multi-frequency instruments were being tested for commercial applications in nuclear steam generators for inspecting tubing. Because when you have a barrier to fission product release like steam generator tubes, it's very important that they don't leak. So in the 70s, 80s, 90s, when a lot of the tubes and steam generators were cracking, there was lots and lots of eddy current testing taking place. And even today, it's part of the U.S. regulations from the Nuclear Regulatory Commission that all your tubes get tested on a periodic basis. Now, even though that most steam generators with cracked tubes have been replaced with more advanced material that doesn't crack, like thermally treated Inconel 690, you still have to test them because even if they don't crack, you may have wear fretting degradation. You may have wear from foreign objects. You could have tube to tube wear. So all those things, can be detected with eddy current testing, and it's very good to find those things early so you can, make repairs, fix the problem. Due to the rapid improvements in technology in recent decades, test instruments have gotten smaller and much, much more powerful than instruments used in the past. So on a 1960, your tester was about the size of a refrigerator, pretty big refrigerator. 1980, that's when the EM3300s, MIS-12s. There was an instrument from Nortec. I forget the name of the model, but it's similar to that 1980 picture there. Then around 2000, that's when everybody was using the laptops. So you get the test instrument, you hook it to a laptop, and then you could have another external display. Back when displays were 30 pounds, 50 pounds. And then on the far right, that's an instrument from Eddy. I believe that's the Ready for surface array testing. But you can see how small it is, and it's self-contained, so you don't need an extra monitor, you don't need a computer. Portable instruments enable NDT inspectors to easily access the various areas of an aircraft needing inspection. Eddy current testing is suited very well for detecting small discontinuities around fasteners and in the thin aluminum aircraft skin. That skin's pretty thin, what is it, a couple millimeters? So it's light and it's strong, but you want it to be structurally sound, free of discontinuities. And eddy current testing is a good way to find those little discontinuities. Large heat exchangers use robotic fixtures to guide the probes into the tubes and mechanical probe drivers to propel multiple probes at once. I would say using dual guide tubes is probably the standard in the United States now. Sometimes 3 guide tubes are used at once, so you can run 3 probes at a time. For a while, they tried to go beyond 3 and run 4, but when you try to run 4 probe pushers going into 4 tubes at once, there seem to be diminishing returns, right? Because one of the probes would go bad, and you'd have to stop and replace it, or maybe one of the tubes had restriction, or maybe had some, debris in it, maybe some sludge, and that would just complicate things for the other 3 probes. So 2 is most popular. Sometimes 3 are used when higher production is needed. These advancements in technology enables nuclear energy companies to inspect hundreds of miles of tubing during a scheduled refueling outage. So a typical refueling outage may have a week allotted to have the steam generator inspections. And if you have 4 steam generators with, let's say, 5,000 tubes, and those tubes are 100 feet long, it's 4 steam generators. If you do the math, I know it's in the hundreds of miles of tubing. Where am I at here? All right, I skipped ahead of a slide here. So many advancements have been made in array probe technology in recent years. Eddy current array probes can use a single band or multiple bands of individual coils, allowing substantially more coverage in a single pass than when conventional single coil probes are used. One of the problems with pencil probes is that the coils are very tiny in diameter. They can be, a couple millimeters in diameter. They can be maybe 6, 7 millimeters in diameter. And, the smaller they are, the more sensitive they are to tiny, tiny cracks. However, one of the requirements when you're using a pencil probe is you have to meticulously scan, in a pattern, back and forth, with sufficient overlap, so you don't miss any flaws. And if you're not paying real close attention, or you're not using some sort of automated fixture to do the scanning, it's actually pretty easy to miss an area of the material. And if you miss an area of the material that happened to have the crack in it, that could lead to catastrophe. So array probes, I think a lot of them now are printed. They can 3D print array probes, and they look like basically like a sheet of paper. And if you look real close at them, you can see all the tiny, tiny coils. Eddy current array probes effectively eliminate the time-consuming roster scanning necessary when pencil probes are used. This has a significant impact on inspection speeds. I remember when I first inspected an aircraft wheel, it was with a pencil probe manual scanning. And I'm telling you, that would take hours to do it right. And then if you redid the test a week later, your scan pattern might be different. You might not even scan all the exact same areas of the wheel. But you can see here, if you use a flexible array probe, you just lay it along the geometry of that wheel and rotate the wheel past it, or rotate the array ribbon across the wheel. It's a much faster exam, and the probability of detection of flaws is much, much higher. Array probes are not only for surface, they are routinely used on internal coils to inspect, or internal probes to inspect tubing. A lot of the probes used for tubing now have bobbin coils, which has been around for many, many decades. But they also incorporate bands of array pancake coils around the circumference. What that does is allow you to get 360-degree resolution around the tube without rotating a probe head through the tube. That's called rotating coil or rotating probes. MRPC used to be the acronym for that, motorized rotating pancake coil. But now, since much of the time plus point coils are used, which are differentially wound, they look like a plus, so you get dual polarity signals. The term now, they've sort of changed the meaning to motorized rotating probe coil. So either one works. Pairing robotic probe delivery systems with array probe technology has even more efficiency. For example, manual eddy current inspection of large aircraft wheels using pencil probes can take several hours, like I said. But if you couple the array probes with robotic fixtures, you can complete large wheel scans in just minutes. Up until the early 1990s, most eddy current inspections were limited to using one probe type at a time. For example, tubing would first be inspected with the bobbin coil probe, and then if they found something they wanted to get a better look at, they would go back into the tube at a later time with a rotating coil or an array probe to provide more information. The nice thing about array probes and rotating probes is that they can generate the terrain plot, the C-scan. And the C-scans allow you to not only see what's happening along the length of the tube, you can also see 360 degrees around the tube. So a typical calibration standard has 4 20% flat bottom holes drilled around the circumference at the same axial extent in the tube. If you run an array probe past that, or a rotating probe, and you do a terrain plot, you can see all 4 holes. With bobbin, you would only get one signal because the bobbin coil and its circling coils average the complete circumference and give you one signal. So since those days, it has become more commonplace to examine test objects using probes containing 2 or more coil types at the same time on the same probe body. This image shows inspection data from a probe containing bobbin coils. That's the 2 listed used on the left there. And an array of surface pancake coils. And for this reason, most tubes do not need to be re-inspected with an additional probe. So in the old days, you'd use bobbin coil, find an indication, want to get more information, you examine it with a rotating probe. But now, since you can deliver the bobbin coils and the array coils on the same probe body, there's really no need to go back and test that tube with anything else, unless the array probe signal that you're evaluating still, lacks some of the dispositioning power of the rotating coil, and you want to get an even better look beyond the array probe, then you would go in and inspect with a rotating probe. Now, there are times if you find a flaw and it's a high impact flaw, so let's say you're examining steam generators and it's the only tube that has a defect in it that requires tube plugging, and the signal's not super straightforward with the bobbin coil or the array probes, but you're going to have to mobilize the repair crew. And that one tube that needs to be plugged, the tube plugging could end up costing, when you consider the time and if you're on a critical path, hundreds of thousands of dollars potentially. So if you're going to make the decision to plug it, you want to be extra sure that it's a legit flaw. So you may have tested it with a bobbin coil, an array probe, a rotating probe, but the customer might want to go look at it with a specialized type of rotating probe. So if you initially examined it with a pancake coil rotating probe, you might want to use a plus point rotating probe, which is differentially wound. So that presents the data a little bit differently. If you're on the plus point and the data is still sort of ambiguous, you might want to go run it with a Ghent probe. Ghent probes are rotating probes that have magnets in them. And what they will do is, if you suspect your data may be influenced from permeability effects in the tube, the Ghent probe does a particularly nice job of suppressing the variables from permeability variations. So a lot of times you'll get in a situation where you want to throw as much probe technology you can at a particular tube just to get all the information that is possible. When using array probes and multiple robotic fixtures, a tremendous amount of data is collected in a short period of time. Refueling outages now are getting shorter and shorter. I think the last I heard is some plants are shooting for like 19-day outages. There's a lot of maintenance that goes on in the refueling outage. And depending on the scope of your heat exchanger exams, they might only be, 2-3 days. But they might still want 100% of the tubes tested in multiple heat exchangers. So that's a lot of data collected in a short period of time. And the increased amount of data volume, coupled with the aging workforce of eddy current analysts around the world, they require further innovation in automated data analysis to be pursued, because there just aren't the people around anymore to analyze the data, especially when there's this much of it coming at you so fast. Nowadays, with the advanced technology and data storage is getting a lot cheaper, you have easy access to archived inspection data, which allows data analysts to display multiple years of inspection data on the Listegy display at the same time. So if you look at this Listegy on the right, that's a very real image that people see when they're analyzing data. And it used to be the tubing, when it came from the tube mill, would have lots and lots of buff marks. And you could have hundreds of buff marks per tube. When they took a little buffing wheel and any place there was a little imperfection on the tube that stuck out a little bit, they would just hit it with the buffing wheel. Well, that would leave a mark on the tube, or would change the material properties such that you'd get some signal from it, but they're normally classified as benign signals. They call them manufacturing burnish marks. But a manufacturing burnish mark can look very similar, to an axial flaw, because they both have some axial extent to them. And the difference between an in-service, flaw that happened during service and it's getting larger over time, that differs from a burnish mark or a buff mark, because the buff marks never change. Cycle after cycle, they look exactly the same. But if you have like a small wear scar signal, the more the tube wears from the support structure, the more your signal will change over time. So when you configure the previous inspection data that you want to look at during your current inspection, let's say you wanted to look at the baseline data, so before the heat exchangers ever went into service, then you want to look at the last time it was inspected, maybe it was 2 years ago, and then you want to look at the data from today. You can configure your system so all three are on the screen at the same time. So as you're scrolling up through the data, every time you go to a signal of interest, it shows all three inspections on the screen at the same time. If it was a buff mark, all of those signals that you see here would look exactly like the one in the upper left. They wouldn't change over time. Well, it's not true. Burnish marks sometimes change after the first cycle of operation due to the thermal operation. So it changes them a little bit, but then after that, they don't change. So for looking at previous history, a lot of times plants will go back to the very first inspection after the heat exchanger had been in operation for one cycle. But the case of this one, when you're looking at 3 years inspection data and the baseline has real high phase, that could be a real small pit, maybe a 10% pit. But if you look at last year's data, it's got less phase. That means it's growing a little bit, getting a little deeper. And then when you look at the current year inspection data, it's standing straight up. So that's a small flaw from the baseline. Something happened in the factory. Maybe got hit with a little drill bit when they were putting it in the shipping cases, the tubes. And then it grew over time as thermal operation, stress, vibration, all that kind of stuff. So it makes it real easy to do these lookups because you're actually doing historical lookups on the fly. In the old days, you have to manually go spin up the tape. I mean, it could take hours to look up some previous indications. Now it's just happening in real time.